Hello and welcome back to Sleepy Maths. I'm so glad you're here. Wherever you're listening from tonight, whether it's tucked beneath warm blankets in a quiet bedroom, curled up on a comfortable couch with the evening light fading outside, or perhaps somewhere peaceful where your mind can wander freely, I'd love to know where you are and what time it is. Feel free to share it in the comments. It's always wonderful to see how these gentle explorations of knowledge drift across time zones like thoughts floating on a calm evening breeze. Before we begin our journey into the fascinating world of probability and decision-making, if you enjoy these soft, deep dives into the mysteries of mathematics and human thinking, I'd be truly grateful if you gave the video a like or even subscribed. It helps keep the lights on and the neurons gently firing, albeit very, very slowly. Tonight, we're going to explore something that has puzzled mathematicians, frustrated game show contestants, and sparked heated debates in academic circles for decades. We'll wander through the elegant landscape of the Monty problem, a deceptively simple puzzle that reveals profound truths about probability, intuition, and the way our minds make sense of uncertainty. From the bright lights of television game shows to the quiet corners of probability theory, we'll discover how a simple choice between three doors opens up entire worlds of mathematical wonder. Now, I do hope this exploration helps you unwind and perhaps drift off to sleep with your mind full of gentle mathematical mysteries. But fair warning, if you find yourself staying awake because it's too intriguing, well, at least you'll wake up a bit wiser about the beautiful complexities of chance and choice. One gentle reminder before we dive in: this video is for educational and entertainment purposes only. It's not intended to provide gambling advice or encourage risky decision-making. If you have concerns about probability in real-world situations, please consult with appropriate professionals. So, take a deep breath, let your shoulders relax, maybe dim the lights just a little, and let's gently wander through the wonderful world of probability, where mathematics meets human psychology in the most surprising ways. We'll start with a simple game show scenario, but like all good mathematical stories, it will take us to places we never expected to go, revealing truths about how we think, how we choose, and how the universe of chance operates in ways that often contradict our deepest intuitions. Picture, if you will, a bright television studio in the 1960s. The lights are hot, the audience is eager, and a man named Monty stands before three doors, each one hiding a secret. Behind one door waits a gleaming new automobile, the prize that every contestant dreams of winning. Behind the other two doors, somewhat less glamorously, stand a pair of goats. Not that goats aren't lovely creatures in their own right, but they're hardly what one hopes to drive home from a game show. This was the world of Let's Make a Deal, and it was here, in this seemingly simple game of chance, that one of mathematics' most beautiful and bewildering puzzles was born. The rules appeared straightforward enough to make any viewer feel confident they understood the game completely. A contestant would choose one of the three doors, knowing that they had a 1 in 3 chance of selecting the car. Mathematics, after all, doesn't lie about such basic probabilities. But then came the twist that would eventually spawn thousands of academic papers, heated arguments, and more than a few bruised egos among very intelligent people. After the contestant made their initial choice, Monty, who knew exactly what lay behind each door, would dramatically open one of the remaining doors to reveal a goat. Not just any door, mind you, but specifically one that he knew contained a goat. This wasn't random chance at work, this was calculated revelation. The goat would stand there, perhaps looking mildly confused about its sudden television debut, while Monty turned to the contestant with that gleaming game show host smile. Then came the question that would echo through decades of mathematical discourse. Would you like to change your mind? The contestant now faced a choice between their original door and the remaining unopened door. To most people, including many very smart people, this seemed like a simple 50-50 proposition. 2 doors, 1 car, equal odds. What could be simpler? Yet this assumption, so reasonable and intuitive, was completely wrong. The truth hiding behind those doors was far more subtle and beautiful than anyone initially realized. When mathematicians first encountered this problem in its formal presentation, many of them fell into the same trap that snared television audiences. The correct answer seemed to defy common sense, which made it all the more fascinating to those who love puzzles where reality refuses to conform to intuition. This was mathematics at its most mischievous, presenting a scenario where the obvious answer was not just wrong, but dramatically wrong. The story of how this simple game show puzzle became one of the most famous problems in probability theory is itself a tale worth telling slowly and carefully. It reveals something profound about how human minds grapple with uncertainty, how mathematical truth sometimes hides in plain sight, and how even very intelligent people can be fooled by problems that seem simpler than they actually are. Let's walk through this puzzle step by step, allowing each stage to unfold naturally like a gentle mathematical story. Imagine yourself as the contestant, standing there under those bright studio lights with 3 doors before you. Door number 1, door number 2, door number 3, each one identical from your perspective, each one hiding its secret. The host explains the rules. 1 car, 2 goats. Make your choice. You point to door number 1, perhaps because you like the symmetry of starting at the beginning, or maybe because 1 is your lucky number. It doesn't matter why you choose it. What matters is that you've now divided the world of possibilities into 2 groups, the door you chose, and the 2 doors you didn't choose. At this moment, your door has a 1/3 probability of hiding the car, while the other 2 doors together have a 2/3 probability. This much seems clear and uncontroversial. Basic probability tells us that when you have 3 equally likely options and you choose one, you have a 1 in 3 chance of being right. Now comes the moment that changes everything, though you might not realize it at first. Monty Hall, with his complete knowledge of what lies behind each door, walks over to the 2 doors you didn't choose. He could open either door number 2 or door number 3, but he doesn't choose randomly. He specifically opens the one that he knows contains a goat. Let's say he opens door number 3, revealing a goat that seems somehow philosophical about its role in this mathematical drama. This action might seem like simple showmanship, but is actually a profound transfer of information. Monty hasn't just shown you a goat, he's used his knowledge to eliminate one of the wrong choices from consideration. This isn't random elimination, it's strategic revelation. The probability that was distributed between doors 2 and 3, that 2/3 chance that the car was behind one of those doors, hasn't evaporated into thin air. Instead, it has collapsed entirely onto door number 2. Think of it this way. Before Monty opened any door, you knew with certainty that at least one of the doors you didn't choose contained a goat. Monty's action in revealing that goat doesn't provide new information about the fundamental structure of the problem. Instead, it clarifies where the probabilities must now reside. If the car was behind door 3, Monty would have had to open door 2 to reveal a goat. If the car was behind door 2, Monty would have had to open door 3. In either case, he's essentially pointing toward the location of the car by eliminating one of the 2 possibilities. The door you originally chose still has that same 1/3 probability it always had. But now, instead of that 2/3 probability being split between 2 doors, it's concentrated entirely on the remaining unopened door. This is why switching doors doubles your chances of winning. You're moving from a 1/3 probability to a 2/3 probability. The reason the Monty Hall problem feels so counterintuitive isn't because people are bad at mathematics. It's because our brains are wired to process certain types of information in ways that served our ancestors well but can mislead us in abstract probability scenarios. When we see 2 doors remaining after one has been opened, our minds naturally want to treat this as a fresh start. A new problem with 2 equally likely outcomes. This isn't stupidity, it's the result of cognitive systems that evolved to make quick decisions based on immediate, visible information. In the ancestral environment, if you were choosing between 2 paths through a forest, and each path looked equally promising, it would make sense to consider them equally likely to lead to safety or success. But the Monty Hall problem isn't really a choice between 2 equivalent options. It's a choice between your original decision and all the other possibilities combined, with the host helpfully eliminating the wrong choices from that second group. Our intuition also rebels against the idea that the host's knowledge changes the fundamental probabilities of the situation. We tend to think of probability as an inherent property of objects or situations, when it's actually a description of our uncertainty given the information we have. When the host opens a door, he's not changing the essential nature of the doors. He's providing information that should change our assessment of where the car is likely to be. This distinction between objective reality and our knowledge of that reality is crucial to understanding many probability problems. But it's not a distinction that our everyday thinking handles naturally. We're more comfortable thinking in terms of what is rather than what we know about what is. This confusion between the map and the territory, between probability and actuality, leads many people to feel that the problem itself is somehow unfair or that there's some sort of mathematical trickery involved. Another psychological factor at work is what researchers call the status quo bias, our natural tendency to stick with decisions we've already made. Once you've chosen door number 1, it becomes your door in a psychological sense. You've invested your choice in it, and changing feels like admitting you were wrong initially. But the Monty Hall problem specifically rewards those who are willing to abandon their initial choice in favor of new information. It's a puzzle that punishes loyalty to your first instinct and rewards flexibility in the face of additional evidence. This goes against some deeply ingrained psychological tendencies, which might explain why even very intelligent people often resist the correct answer when they first encounter it. The problem seems to be testing not just your mathematical reasoning but also your willingness to let go of decisions you've already made when new information suggests they might not be optimal. There's also the challenge of thinking in terms of processes rather than just outcomes. When we see 2 doors remaining, we naturally focus on the current state of the game rather than the process that led to this state. But the history of how we arrived at this moment is crucial to understanding the probabilities involved. The door you chose was selected before any information was revealed. The remaining door is the survivor of a process where the host used his knowledge to eliminate wrong choices. These doors might look equivalent now, but their mathematical pedigrees are entirely different. Learning to think about probability in terms of processes and information flows, rather than just final states, is one of the key insights that the Monty Hall problem teaches us. To truly understand why switching doors is the optimal strategy, we need to dive deeper into the mathematical structure underlying this deceptively simple problem. Let's approach it from several different angles, each one illuminating a different aspect of the beautiful mathematical truth at the heart of the puzzle. First, consider the problem from the perspective of conditional probability, one of the most powerful tools in the probabilist's toolkit. Initially, the probability that the car is behind your chosen door is 1/3, and the probability that it's behind one of the other 2 doors is 2/3. When the host opens one of those other doors to reveal a goat, he's not changing these fundamental probabilities, he's providing information that allows us to update our understanding of where that 2/3 probability is concentrated. The technical term for this kind of updating is Bayesian reasoning, named after the 18th century mathematician Thomas Bayes, who developed formal methods for revising probability estimates based on new evidence. Let's work through the mathematics explicitly. Before any doors are opened, the probability that the car is behind door 1 is 1/3. The probability it's behind door 2 is 1/3. And the probability it's behind door 3 is also 1/3. Now, suppose you choose door 1 and the host opens door 3 to reveal a goat. We want to calculate the probability that the car is behind door 2, given that the host opened door 3. This is written as P of car behind door 2, given host opens door 3, using Bayes' theorem. This conditional probability depends not just on the original probability that the car was behind door 2, but also on the probability that the host would open door 3, depending on where the car actually is. If the car is behind door 1, the host could open either door 2 or door 3, each with probability 1/2. If the car is behind door 2, the host must open door 3. That happens with probability 1. But if the car is behind door 3, the host cannot open door 3. The probability is 0. When we work through these numbers using Bayes' rule, we find that the updated probability that the car is behind door 2, given that the host opened door 3, is 2/3. Another way to see this is through the lens of information theory. Initially, you have a certain amount of uncertainty about where the car is located. This uncertainty can be quantified using the concept of entropy, which measures how much information is needed to resolve uncertainty. When the host opens a door, he's providing information that reduces the total uncertainty in the system, but this information reduction isn't distributed equally among all possibilities. The door you originally chose receives no new information. Its probability remains unchanged at 1/3, but the remaining unopened door receives all the information that was previously distributed between it and the door that was just opened. This is why the remaining door's probability jumps to 2/3. The host has essentially performed an information transfer, concentrating probability onto one of the doors you didn't originally choose. We can also approach this problem through symmetry arguments, which often provide the most elegant insights in mathematics. Consider what happens if you always follow the strategy of switching doors. There are 3 equally likely scenarios for where the car is actually located: behind door 1, behind door 2, or behind door 3. If you always choose door 1 initially and then switch, you win in scenarios 2 and 3, and lose only in scenario 1. This gives you a 2/3 probability of winning. Conversely, If you always stick with your initial choice, you win only in scenario 1 and lose in scenarios 2 and 3, giving you a 1/3 probability of winning. The symmetry of the problem ensures that these probabilities don't depend on which specific door you choose initially, or which specific door the host opens. The structure of the game guarantees that switching is always the better strategy. One of the most illuminating ways to understand the Monty Hall problem is to imagine it with a much larger number of doors. This scaling exercise often provides the aha moment that makes the counterintuitive answer suddenly seem obvious. Let's suppose that instead of 3 doors, we have 100 doors. Behind one of them is a magnificent sports car, and behind the other 99 are goats of various temperaments and colors. You're asked to choose one door out of the 100. Clearly, the probability that you've chosen correctly is a mere 1%, while the probability that the car is behind one of the other 99 doors is 99%. Most people feel comfortable with this assessment. With so many doors, it seems almost certain that your initial guess is wrong. Now comes the crucial moment. The host, who knows exactly where the car is hidden, begins opening doors from among the 99 you didn't choose. One by one, he reveals goats, carefully avoiding the door that actually contains the car. He opens one door, revealing a goat, then another door, another goat. He continues this process, revealing goat after goat, until he has opened 98 of the 99 doors you didn't choose. Now only 2 doors remain in the game, the one you originally selected, and one lone survivor from the original group of 99. The host turns to you with that familiar question: would you like to switch? In this scenario, most people immediately recognize that switching is the obvious choice. Your original door still has only a 1% chance of hiding the car, while the surviving door from the group of 99 must have a 99% chance. This scaling exercise reveals something beautiful about the underlying mathematics of the problem. The host's knowledge and his systematic elimination of wrong choices effectively concentrates all the probability that was originally distributed among the doors you didn't choose onto the single remaining door from that group. It doesn't matter whether that group originally contained 2 doors or 99 doors, the same mathematical principle applies. The host is essentially offering you the choice between your original single door and the best possible door from all the alternatives, with his knowledge used to identify which door that is. When we scale the problem up, this asymmetry between your original choice and the optimized alternative becomes much more apparent, but the mathematical structure is identical in both the 3-door and 100-door versions. The scaling exercise also helps us understand why our intuition fails us in the original 3-door version. With 3 doors, the difference between a 1/3 and 2/3 probability, while mathematically significant, doesn't feel as dramatic as the difference between 1% and 99%. Our psychological machinery for dealing with uncertainty seems to be less sensitive to probability differences when the numbers involved are closer to 50%. This might be an artifact of how our brains evolved to deal with situations where outcomes were often close to even odds. In many survival situations, you either succeed or fail, find food or don't, escape danger or don't. Our intuitive probability systems may be calibrated for these binary scenarios rather than for the more subtle probability distributions that arise in formal mathematical problems. The Monty Hall problem might have remained an obscure mathematical curiosity discussed only in probability textbooks and statistics classrooms if not for one of the most famous intellectual controversies of the late 20th century. In September 1990, a reader wrote to Marilyn vos Savant, who at the time held the Guinness World Record for highest IQ and wrote a popular column called Ask Marilyn in Parade magazine. The reader presented the Monty Hall problem in its classic form and asked whether a contestant should switch doors. Vos Savant gave the correct answer: yes, you should switch, because switching doubles your probability of winning from 1/3 to 2/3. What happened next became a fascinating case study in how even brilliant minds can be deceived by counterintuitive problems, and how intellectual humility is just as important as raw intelligence when grappling with complex questions. The response to vos Savant's column was swift and overwhelmingly negative. Her office was flooded with thousands of letters, many from people with impressive academic credentials, telling her in no uncertain terms that she was wrong. Mathematics professors, PhD holders, and other intellectuals wrote lengthy explanations of why they believed the answer should be 50-50. Some letters are merely corrective, but many were condescending or even hostile. "You blew it," wrote Robert Sachs, a mathematics professor at George Mason University. "As a professional mathematician, I'm very concerned with the general public's lack of mathematical skills. Please help by confessing your error. Another correspondent, Scott Smith, who held a PhD from the University of Florida, wrote, "There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more." Shent, the controversy revealed something uncomfortable about the relationship between intelligence, expertise, and mathematical truth. What made this controversy particularly fascinating was not just that so many intelligent people got the problem wrong initially, but how they responded when presented with the correct analysis. Vos Savant, to her credit, didn't simply dismiss her critics or retreat behind her impressive IQ score. Instead, she devoted several subsequent columns to explaining the problem from multiple angles, providing different ways of thinking about the mathematics involved. She suggested that readers could verify the answer by running simulations, either with physical cards and dice or with computer programs. She explained the problem using the 100-door variation, which often made the correct answer more intuitive. Gradually, as people worked through these explanations and ran their own experiments, many of the original critics began to change their minds. The same Professor Sachs who had written that scathing initial letter later sent a follow-up. "After removing my foot from my mouth, I'm now eating humble pie. It's been an intense professional embarrassment." The controversy also highlighted some troubling undercurrents about gender and intellectual authority. Several letters to Vos Savant included comments suggesting that women might think about mathematics differently than men, or questioning whether someone without formal mathematical training should be writing about probability theory. These responses revealed biases that went beyond mere mathematical disagreement and touched on deeper questions about who is considered a legitimate mathematical authority. Vos Savant herself noted that the problem seemed to be particularly challenging for people who were accustomed to being the smartest person in the room. Perhaps the counterintuitive nature of the problem was especially threatening to those whose identity was closely tied to their mathematical abilities. The controversy became not just a debate about probability theory, but a lesson in intellectual humility and the importance of being willing to revise one's beliefs when presented with compelling evidence. One of the beautiful aspects of the Monty Hall problem is that its abstract mathematical truth can be verified through concrete experimentation, unlike many theoretical problems in mathematics. This puzzle can be tested using simple simulations that anyone can run, either with physical materials or computer programs. These experiments provide a bridge between mathematical proof and empirical observation, allowing people to see the correct answer in action rather than just understanding it intellectually. Many people who resist the mathematical arguments find themselves convinced when they watch the results of repeated trials unfold before their eyes. There's something profoundly satisfying about seeing mathematical truth emerge from the accumulation of experimental evidence. The simplest simulation involves nothing more than 3 playing cards. 2 red cards representing goats and 1 black card representing the car. Shuffle the cards face down, then follow the Monty Hall protocol. Choose 1 card, have a friend playing the role of the host, flip over one of the remaining red cards, then decide whether to stick with your original choice or switch to the other remaining card. Repeat this process 50 or 100 times, keeping track of how often the switching strategy wins versus how often the staying strategy wins. What you'll observe, if you run the experiment long enough, is that switching wins approximately twice as often as staying. The exact ratio will vary due to random fluctuation, but the pattern becomes clear as the number of trials increases. This convergence from random variation toward mathematical truth is itself one of the beautiful phenomena that probability theory explains. The law of large numbers guarantees that experimental frequencies will approach theoretical probabilities as sample sizes grow. Computer simulations allow for even more extensive testing of the problem. A simple program can run millions of trials in seconds, providing overwhelming empirical evidence for the mathematical analysis. Such simulations can also explore variations of the basic problem. What happens if there are 4 doors instead of 3? What if the host doesn't always know where the car is? What if there are 2 cars instead of 1? These computational experiments help deepen our understanding of the mathematical structures underlying the original problem, and show how the basic insights extend to more complex scenarios. They also provide a way for people who are uncomfortable with formal mathematical proofs to gain confidence in probability theory through direct observation of its predictions. The experimental approach to the Monty Hall problem also illustrates a fundamental principle of scientific thinking. When theory and intuition conflict, we can often resolve the disagreement through careful observation. This is the same methodology that has driven scientific progress for centuries, from Galileo's experiments with falling objects to modern particle physics research. Mathematics provides the theoretical framework for understanding probability, but experiments provide the empirical verification that our mathematical models actually describe reality accurately. In the case of the Monty Hall problem, the harmony between mathematical analysis and experimental results gives us confidence that we truly understand what's happening in this deceptively simple game of doors and choices. The Monty Hall problem serves as a window into the broader landscape of cognitive biases that influence human decision-making. Our brains, evolved for survival in environments very different from modern mathematical puzzles, employ shortcuts and heuristics that can lead us astray when dealing with abstract probability problems. Understanding these biases helps explain not only why the Monty Hall problem feels counterintuitive, but also why humans systematically make predictable errors in many other situations involving uncertainty and choice. The study of these cognitive biases has become a rich field of research spanning psychology, economics, and decision science, revealing the fascinating interplay between human psychology and mathematical reasoning. One of the most relevant biases for understanding the Monty Hall problem is what psychologists call the equiprobability bias or equal likelihood heuristic. When faced with multiple options, especially when we lack specific information about them, our minds tend to assign equal probabilities to each possibility. This mental shortcut works well in many everyday situations, but it can mislead us in scenarios where the options are not actually equivalent. In the Monty Hall problem, the two remaining doors after the host's revelation look equivalent from a superficial perspective, leading our minds to treat them as equally likely to hide the car. But as we've seen, their mathematical histories are quite different, and this difference is crucial to calculating the correct probabilities. Another important bias is what researchers call anchoring, the tendency for initial information to heavily influence subsequent judgments. When you first choose a door in the Monty Hall problem, that choice becomes an anchor that affects how you think about the rest of the game. The 1/3 probability associated with your initial choice feels fixed and unchangeable, making it difficult to recognize that switching to the other door gives you access to the 2/3 probability that was originally distributed among the doors you didn't choose. This anchoring effect is compounded by what's known as the endowment effect, our tendency to value things more highly simply because we own them or have chosen them. Your initial door choice becomes yours in a psychological sense, making it emotionally difficult to abandon even when rational analysis suggests you should. The Monty Hall problem also illustrates the base rate neglect, a common error where people focus on specific information while ignoring broader statistical patterns. When the host opens a door to reveal a goat, this specific piece of information tends to overwhelm our consideration of the base rates, the fundamental probabilities that govern the problem. We focus on the immediate situation, two doors with one car between them, rather than considering the broader context of how we arrived at this situation. This bias appears in many real-world contexts, from medical diagnosis to criminal justice, where specific case details can distract from relevant statistical information about broader patterns and probabilities. The basic Monty Hall problem, elegant as it is, represents just one member of a large family of related probability puzzles. Exploring variations of the original problem helps deepen our understanding of the underlying mathematical principles, while also revealing how subtle changes in setup can dramatically alter the optimal strategy. These variations also demonstrate the power of mathematical thinking to illuminate unexpected connections between seemingly different problems. Each variation teaches us something new about probability, information, and decision-making, while also showing how robust or fragile the insights from the original problem prove to be when the rules change. Consider, for instance, what happens if we change the number of doors. With 4 doors, 1 car, and 3 goats. Suppose you choose 1 door, and the host then opens 2 doors to reveal 2 goats. Should you stick with your original choice, or switch to the remaining door? The mathematical analysis follows the same pattern as the original problem. Your initial choice has a 1/4 probability of being correct, while the remaining door inherits the 3/4 probability that was originally distributed among the 3 doors you didn't choose. The host's knowledge allows him to concentrate this probability onto a single door by eliminating the wrong choices, so switching is still the optimal strategy, and it's even more advantageous than in the 3-door version because the probability gain from switching is larger. More interesting variations arise when we change the host's knowledge or behavior. What if the host doesn't always know where the car is hidden? Suppose that sometimes the host accidentally opens the door with the car behind it, ending the game immediately. In such cases, the mathematical analysis becomes more complex because we must account for the probability that the game continues to the switching decision point. If the host opens doors randomly from among the doors you didn't choose, then conditioning on the fact that the game has continued past his door opening changes the probabilities in subtle ways. The switching advantage persists but is reduced compared to the case where the host has perfect knowledge. Another fascinating variation involves changing the host's motivations. In the original problem, we assume the host wants to give you the best possible chance of winning, or at least that he follows a consistent protocol that doesn't depend on where the car actually is. But what if the host is trying to minimize your chances of winning? If the host knows where the car is and wants you to lose, he might adopt a strategy of always opening a door when you've initially chosen correctly, thereby encouraging you to switch away from the car. In this adversarial version, the optimal strategy flips. You should always stick with your initial choice. This variation highlights how the solution to probability problems can depend not just on the mechanical rules of the game, but also on the incentives and knowledge of other players involved. The Monty Hall problem belongs to a special category of mathematical puzzles where the correct answer violates most people's intuitive expectations. These counterintuitive problems reveal the limitations of human probabilistic reasoning, while simultaneously showcasing the surprising and beautiful results that emerge from careful mathematical analysis. Perhaps the most famous example in this category, aside from the Monty Hall problem itself, is the birthday paradox, a probability puzzle that has amazed and confused people for generations. Like the Monty Hall problem, the birthday paradox demonstrates how mathematical truth can hide behind assumptions that seem obviously correct but are actually deeply flawed. The birthday paradox asks a deceptively simple question. In a group of people, how large does the group need to be before there's a better than 50% chance that two people share the same birthday? Most people's intuitive answer is somewhere around 180 to 200 people, reasoning that since there are 365 days in a year, you need roughly half that many people to have a good chance of a collision. This intuition seems so reasonable that the correct answer feels almost like a mathematical joke. You need only 23 people to have a better than 50% chance of a shared birthday. With 30 people, the probability rises to about 70%, and with 50 people, you're virtually guaranteed to find a birthday match. The key insight that makes this result comprehensible is to think about the problem in terms of pairs rather than individuals. With 23 people, there are 33 different pairs of people who might share a birthday. Each pair has a small probability of sharing a birthday. But when you add up all these small probabilities across all possible pairs, the cumulative probability becomes substantial. This is another example of how focusing on the right mathematical structure can transform a problem from incomprehensible to obvious. Just as the Monty Hall problem becomes clear when you think about it in terms of concentrating probability rather than comparing individual doors, the birthday paradox becomes understandable when you shift perspective from individuals to pairs. The connection between these problems goes deeper than their shared counterintuitiveness. Both problems demonstrate the importance of conditioning on relevant information when calculating probabilities. In the Monty Hall problem, we must condition on the host's knowledge and his systematic elimination of wrong choices. In the birthday paradox, we must think carefully about what it means for birthdays to be randomly distributed and how multiple opportunities for matching affect the overall probability. Both problems also show how human intuition, which works reasonably well for simple probability scenarios, can fail dramatically when dealing with more complex probabilistic structures involving multiple interacting events or conditional information. These counterintuitive probability problems serve an important pedagogical function beyond their entertainment value. They humble us about the reliability of intuitive reasoning while simultaneously demonstrating the power of mathematical analysis to reveal hidden truths about the world. They teach us to be suspicious of our first instincts when dealing with uncertainty and to appreciate the value of formal mathematical tools for navigating complex probabilistic landscapes. Perhaps most importantly, they show us that the universe of mathematical truth is far stranger and more wonderful than our everyday experience would suggest. To truly appreciate the mathematical depth of the Monty Hall problem, we need to explore it through the lens of information theory, a field that quantifies how much information is contained in messages, events, and decisions. This perspective reveals the Monty Hall problem as fundamentally a story about information, how it's distributed, how it's revealed, and how its revelation changes our understanding of uncertain situations. Information theory, developed by Claude Shannon in the 1940s, provides powerful tools for analyzing exactly what happens when the host opens a door and why this action should change our assessment of where the car is likely to be hidden. The mathematical machinery of information theory transforms an intuitive puzzle into a precise scientific question about uncertainty and knowledge. The concept of entropy lies at the heart of information theory. Entropy measures the amount of uncertainty in a situation. High entropy means high uncertainty, while low entropy means low uncertainty. Initially, when faced with 3 doors that might hide the car, the situation has maximum entropy because each door is equally likely to be correct. Mathematically, this entropy can be calculated as the negative sum of each probability times the logarithm of that probability. With 3 equally likely options, the entropy works out to log 3, which is approximately 1/5 to 8 bits of uncertainty. This number represents how much information would be needed, on average, to resolve the uncertainty completely. When the host opens a door to reveal a goat, he's providing information that reduces the total entropy of the system, but this information isn't distributed equally among the remaining possibilities. The door you originally chose receives no new information. From your perspective, its probability remains unchanged at 1/3, but the remaining unopened door receives all the information that was previously shared between it and the door that was just opened. This asymmetric distribution of information is what creates the switching advantage. In information theoretic terms, the host has performed a measurement on the system that collapses the uncertainty in a very specific way, concentrating the remaining uncertainty onto one particular door, while leaving your original choice unchanged. This information theoretic perspective helps explain why the Monty Hall problem feels so counterintuitive. Our brains tend to treat the revelation of a goat as information that affects all remaining doors equally, reducing our uncertainty about each door by the same amount. But the mathematical structure of the problem ensures that the information is distributed asymmetrically. The host's knowledge acts as a filter that directs information towards specific outcomes while leaving others unchanged. Understanding this asymmetric flow of information is crucial for solving not just the Monty Hall problem, but many other probability puzzles where additional information becomes available during the course of the problem. The information theoretic approach also provides a framework for understanding variations of the Monty Hall problem. When we change the number of doors, the host's knowledge, or the rules of revelation, we're essentially changing how information flows through the system and how uncertainty gets redistributed among the remaining possibilities. This mathematical lens transforms what might seem like a collection of unrelated probability puzzles into a unified theory about information, knowledge, and uncertainty. The Monty Hall problem can also be viewed through the sophisticated lens of game theory, the mathematical study of strategic interactions between rational decision makers. While the classic presentation treats the host as a neutral figure following fixed rules, game theory asks deeper questions. What if the host has his own motivations? What if you don't know exactly what those motivations are? What if the host is trying to maximize or minimize your chances of winning? These questions transform the Monty Hall problem from a pure probability puzzle into a rich strategic game where psychology, information, and mathematical reasoning all play crucial roles. Game theory reveals hidden layers of complexity beneath the seemingly simple surface of choosing between doors. In the standard Monty Hall scenario, we assume the host follows a consistent protocol. He always opens a door with a goat. He chooses randomly if he has multiple goat doors to choose from, and his choice doesn't depend on where the car actually is. Under these assumptions, the host isn't really a strategic player. He's more like a mechanical device that reveals information according to predetermined rules. But what if we relax these assumptions? Suppose the host sometimes deviates from the protocol, perhaps opening a goat door when you've chosen correctly but revealing the car when you've chosen incorrectly. In this scenario, the fact that the host has opened a goat door provides evidence that you probably chose correctly initially, completely reversing the optimal strategy. Even more interesting scenarios arise when we consider the host as a strategic player with incomplete information about your decision-making process. Suppose the host knows where the car is but doesn't know whether you understand the optimal strategy. If he wants to maximize your chances of winning, perhaps because the show benefits from happy contestants, he might adopt different revelation strategies depending on whether he thinks you'll switch or stay. Against a contestant who always stays, the host gains nothing by opening any particular door. But against a contestant who always switches, the host can guarantee a win by making sure his door opening doesn't eliminate the car. These strategic considerations introduce a fascinating layer of psychological game playing on top of the basic probability calculations. The game theoretic perspective also illuminates real-world applications of Monty Hall-style reasoning. In negotiations, auctions, and other strategic interactions, participants often have private information that they reveal selectively to influence others' decisions. Understanding when such revelations provide genuine information versus strategic misdirection requires the same kind of careful analysis that solves the Monty Hall problem. A negotiator who reveals some of their private information might be genuinely trying to facilitate agreement, or they might be strategically manipulating your beliefs about the situation. Game theory provides tools for analyzing these scenarios and determining optimal responses to strategic information revelation. The intersection of probability and game theory in the Monty Hall problem also highlights the importance of common knowledge and mutual understanding of the rules. The standard solution assumes that both you and the host understand the game's structure and that this understanding is common knowledge between you. If you're not sure whether the host knows where the car is, or if the host isn't sure whether you understand the optimal strategy, the analysis becomes much more complex. These considerations of higher-order beliefs about beliefs, are central to modern game theory and show how even simple-seeming problems can hide sophisticated layers of strategic reasoning. The mathematical tools we use to solve the Monty Hall problem, particularly Bayesian reasoning about conditional probabilities, have applications far beyond game shows and probability puzzles. In fact, Bayesian thinking represents one of the most powerful frameworks humans have developed for making rational decisions under uncertainty. Every time we update our beliefs based on new evidence, we're performing a kind of Bayesian calculation, whether we realize it or not. The Monty Hall problem serves as an accessible introduction to this broader family of reasoning techniques that can improve decision-making in countless real-world situations, from medical diagnosis to investment strategies to everyday judgment calls. Consider medical diagnosis, one of the most important applications of Bayesian reasoning. When a doctor observes symptoms or receives test results, she's essentially collecting evidence that should update her beliefs about what condition the patient might have, just as the host's revelation of a goat should update our beliefs about where the car is hidden. A positive test result should update a doctor's beliefs about the probability that a patient has a particular disease. But this updating must be done carefully, taking into account not just the test result itself, but also the base rate of the disease in the population and the accuracy characteristics of the test. Many medical errors occur when doctors focus too heavily on test results while ignoring base rate, leading to overdiagnosis of rare conditions. The same Bayesian principles apply to financial decision-making and risk assessment. When an investor receives news about a company, she must update her beliefs about the company's value, but this updating should depend not just on the news itself, but also on the prior probability distribution of possible company values and the reliability of the news source. An earnings report that seems surprising might actually be quite predictable when viewed in the context of the company's historical performance and current market conditions. Investors who understand Bayesian reasoning are better equipped to distinguish between news that genuinely changes the fundamental prospects of an investment and noise that merely creates short-term price movements. Even in everyday social interactions, we constantly perform informal Bayesian updates. When a friend is late for a meeting, we unconsciously update our beliefs about what might have happened based on our prior knowledge of that friend's reliability, the typical traffic conditions, and any other relevant contextual information. Someone who is habitually punctual being late provides stronger evidence that something unusual occurred than the same lateness from someone who frequently runs behind schedule. These informal probability calculations help us navigate social relationships and make appropriate responses to unexpected events. The key insight from Bayesian reasoning is that rational belief updating requires considering both new evidence and prior probabilities. This dual focus helps explain why the Monty Hall problem feels counterintuitive. We tend to focus heavily on the new evidence, the host opening a door, while neglecting the prior probabilities, the original 1/3 chance that we chose correctly. Learning to think like a Bayesian, weighing both priors and evidence appropriately, can improve judgment across many domains of life, from personal relationships to professional decisions to understanding complex social and political issues. Beneath the mathematical surface of the Monty Hall problem lies a rich philosophical landscape concerning the nature of probability itself. What does it mean to say that a door has a 2/3 probability of hiding a car? Is probability an objective feature of the world, or is it merely a description of our subjective uncertainty? These questions have occupied philosophers and mathematicians for centuries, and the Monty Hall problem provides a fascinating case study for exploring different philosophical approaches to probability and their practical implications. The way we interpret probability affects not just how we solve mathematical puzzles, but how we understand scientific reasoning, make decisions under uncertainty, and think about the relationship between knowledge and reality. The classical or frequentist interpretation of probability treats it as a long-run frequency. To say that a door has a 2/3 probability of hiding the car means that if we played the game many times under identical conditions, the car would be behind that door in approximately 2/3 of the cases. This interpretation grounds probability in objective, observable facts about the world, making it amenable to empirical testing through repeated experiments. The frequentist approach provides the theoretical foundation for much of classical statistics in scientific methodology, offering a way to connect mathematical probability theory with concrete experimental observations. However, the frequentist interpretation faces challenges when applied to unique, non-repeatable events. What does it mean to assign a probability to a specific door in a single game show episode? We can't repeat that exact scenario multiple times to observe long-run frequencies. This limitation has led some philosophers and mathematicians to embrace subjective or personalist interpretations of probability. From this perspective, probability represents the degree of belief that a rational agent should have given the available evidence. The 2/3 probability assigned to the remaining door reflects not an objective property of that door, but rather the appropriate level of confidence that a well-informed rational agent should have about where the car is located. The Bayesian interpretation of probability, named after Thomas Bayes, provides a mathematical framework for the subjective approach. Bayesian probability theory describes how rational agents should update their beliefs when new evidence becomes available, using tools like Bayes' theorem to calculate appropriate posterior probabilities from prior beliefs and likelihood functions. In the Monty Hall problem, Bayesian analysis shows exactly how the host's action should change a rational agent's degree of belief about where the car is hidden. This approach handles unique events naturally, since it doesn't require imagining infinite repetitions of identical scenarios. A third philosophical approach, the logical interpretation, attempts to find middle ground between objective and subjective views of probability. According to this view, probability represents a logical relationship between evidence and conclusions, similar to how deductive logic represents relationships between premises and conclusions. The probability that the car is behind a particular door is determined by the logical structure of the evidence, independent of any individual's beliefs or long-run frequencies. This interpretation appeals to those who want probability to have objective content without requiring infinite repetitions of identical scenarios. The advent of modern computing has revolutionized how we explore and understand probability problems like the Monty Hall puzzle. What once required sophisticated mathematical analysis can now be investigated through brute force simulation, allowing students and researchers to observe probability theory in action rather than simply accepting mathematical proofs. Computational approaches provide an invaluable bridge between abstract theory and concrete experience, making complex probabilistic concepts accessible to those who might struggle with formal mathematical arguments. They also enable exploration of variations and extensions that would be difficult to analyze analytically, opening up new avenues for understanding the deep structures underlying probability and decision-making. A simple computer simulation of the Monty Hall problem requires only basic programming concepts: random number generation, conditional logic, and counting. The computer can play the role of all participants in the game, randomly placing the car behind one of 3 doors, simulating the contestant's initial choice, having the host reveal a goat according to the standard protocol, and then implementing either the staying or switching strategy. By running this simulation thousands or millions of times, we can observe the long-run frequencies that theory predicts. Staying wins approximately 1/3 of the time, while switching wins approximately 2/3 of the time. These simulations provide compelling empirical evidence for the mathematical analysis, often convincing skeptics who remain unmoved by theoretical arguments. More sophisticated simulations can explore the effects of varying different parameters of the problem. What happens if the host doesn't always know where the car is? How do the probabilities change if there are 4 doors instead of 3? What if the host has a slight bias toward opening certain doors when he has multiple options? Computer simulations can answer these questions quickly and accurately, generating data that would be impossible to collect through physical experiments. They also allow for exploration of edge cases and boundary conditions that help deepen our understanding of the underlying mathematical structures. The computational approach also enables investigation of more complex variants that resist analytical solution. For instance, we might imagine a version where there are multiple rounds of door opening, or where the contestant can choose how many doors the host should open, or where there are multiple cars and goats distributed among the doors. These scenarios quickly become mathematically intractable, but computer simulations can provide insight into optimal strategies and expected outcomes. Such explorations often reveal surprising patterns and suggest new theoretical questions for mathematical investigation. Modern machine learning techniques add another dimension to computational exploration of the Monty Hall problem. We might train an artificial neural network to play the game optimally, then analyze how the network's internal representations capture the relevant probabilistic relationships. Or we could use reinforcement learning algorithms to discover optimal strategies for complex variants of the problem, potentially finding solutions that human mathematicians haven't considered. These approaches blur the line between simulation and discovery, using computational power not just to verify known results but to generate new insights about probability and decision-making. The Monty Hall problem has become a favorite subject for psychological research investigating how humans reason about probability and make decisions under uncertainty. Decades of experimental studies have revealed fascinating patterns in how people approach the problem, what factors influence their likelihood of choosing the optimal strategy, and how these patterns relate to broader questions about human rationality and cognitive bias. These studies provide a unique window into the mechanisms of human reasoning, showing both the remarkable capabilities and systematic limitations of our cognitive systems when dealing with complex probabilistic information. Early psychological studies of the Monty Hall problem focused on simply documenting how often people choose the optimal switching strategy when presented with the problem for the first time. The results were striking. Depending on how the problem was presented, anywhere from 80 to 95% of participants initially chose to stay with their original door rather than switch. This finding was particularly notable because it occurred even among highly educated participants, including graduate students in mathematics and statistics. The prevalence of the suboptimal choice suggested that the error was not due to lack of intelligence or education, but rather reflected something fundamental about how human minds process probabilistic information. Subsequent research investigated what factors could increase people's likelihood of choosing the optimal strategy. One important finding was that concrete, physical presentations of the problem led to better performance than abstract verbal descriptions. When participants could actually see 3 boxes or doors and watch one being opened, they were more likely to switch than when the problem was presented as a word problem. This suggested that the spatial and visual aspects of the situation provided helpful cues that abstract presentations missed. Similarly, studies found that allowing participants to play the game repeatedly, observing the outcomes of their choices, led to gradual improvement in strategy selection over time. Researchers also discovered that small changes in how the problem was framed could dramatically affect people's responses. When the problem was presented in terms of keeping versus trading doors, fewer people chose to switch than when it was presented in terms of choosing between 2 specific doors. The social context also mattered. People were more likely to switch when they imagined themselves as contestants on a game show than when they thought about the problem as an abstract mathematical puzzle. These framing effects revealed that human decision-making in probabilistic context is highly sensitive to contextual cues that shouldn't affect the underlying mathematical analysis. Perhaps most intriguingly, some studies investigated whether understanding the Monty Hall problem predicts performance on other probabilistic reasoning tasks. The results were mixed. While people who solved the Monty Hall problem correctly were somewhat more likely to perform well on related probability problems, the correlation was weaker than might be expected. This suggested that probabilistic reasoning might be more domain-specific than previously thought, with people developing separate intuitions for different types of uncertainty, rather than acquiring general probability skills that transfer broadly across contexts. The Monty Hall problem has become a staple of probability education at all levels, from elementary schools to graduate programs in mathematics and statistics. Its combination of simplicity and counterintuitiveness makes it an ideal vehicle for teaching fundamental concepts about probability, conditional reasoning, and the importance of careful mathematical analysis. However, effectively using the problem as a teaching tool requires careful consideration of how to present it, what common misconceptions to address, and how to help students develop genuine understanding rather than mere memorization of the correct answer. Educational research has revealed both the potential and the pitfalls of using counterintuitive problems like this one in mathematics instruction. One of the most valuable aspects of the Monty Hall problem as a teaching tool is its ability to demonstrate the difference between intuitive and mathematical reasoning. Many students arrive at probability courses with the implicit belief that their intuitive sense of likelihood is generally reliable. The Monty Hall problem provides a gentle but clear counterexample to this belief, showing students that mathematical analysis can reveal truths that contradict even strong intuitive convictions. This revelation can be unsettling initially, but it often motivates students to engage more seriously with formal mathematical methods rather than relying solely on gut feelings about probabilistic situations. The problem also serves as an excellent introduction to conditional probability and Bayesian reasoning. The key insight that the host's knowledge changes how we should interpret his actions provides a concrete example of how probabilities can be conditional on available information. Students who master this insight in the context of the Monty Hall problem are better prepared to understand more complex applications of conditional probability in statistics, science, and decision theory. The problem's concrete setting makes these abstract concepts more accessible than they would be in purely theoretical presentations. However, educational research has also revealed potential pitfalls in using the Monty Hall problem for instruction. Students who are simply told the correct answer without working through the reasoning themselves often fail to understand the underlying principles and cannot apply the same reasoning to related problems. Even worse, some students develop the misconception that probability problems are inherently tricky or counterintuitive, leading them to distrust their reasoning abilities in situations where intuition might actually be helpful. Effective pedagogy requires helping students understand not just why switching is optimal in the Monty Hall problem, but also what features of the problem lead to this counterintuitive result. The most successful educational approaches to the Monty Hall problem typically combine multiple pedagogical strategies. Students might begin by playing physical versions of the game to develop intuitive familiarity with the setup. They might then run computer simulations to observe the long-run frequencies that theory predicts. Mathematical analysis comes later, building on this experiential foundation to provide formal justification for the patterns they've observed. Throughout this process, instructors emphasize the general principles of probability theory that the problem illustrates, helping students develop transferable skills rather than isolated knowledge about a specific puzzle. While the Monty Hall problem might seem like an abstract mathematical curiosity, its underlying principles appear in many practical situations where decision-makers must choose between alternatives based on partial information that gets revealed over time. Understanding these real-world applications helps bridge the gap between classroom probability theory and the complex decisions that people face in business, medicine, science, and everyday life. The mathematical insights from the Monty Hall problem provide valuable guidance for navigating situations where initial choices can be revised in light of new information, and where the source and motivation behind that new information affects its significance. In medical diagnosis, doctors often face scenarios remarkably similar to the Monty Hall problem. A patient presents with symptoms that could indicate several different conditions. Based on initial examination, the doctor forms a preliminary hypothesis about the most likely diagnosis. Additional tests then rule out some possibilities while leaving others open. The question becomes, should the doctor stick with her initial hypothesis, or should she shift toward one of the alternatives that hasn't been eliminated? The optimal strategy depends on understanding how the test results should update the prior probabilities of different diagnoses, taking into account not just what the tests revealed, but also what they failed to reveal. Financial markets provide another rich domain for applying Monty Hall-style reasoning. An investor researches several potential investments and initially favors one based on available information. Over time, new information emerges about some of the investments, perhaps negative news that eliminates certain options from consideration. The question becomes whether the investor should stick with her original choice or switch to one of the alternatives that hasn't been tainted by negative news. The optimal strategy depends on understanding whether the negative news represents random bad luck or systematic problems that might affect all similar investments. Just as the Monty Hall problem requires thinking carefully about why the host opened a particular door, investment decisions require thinking carefully about why particular information became available. Scientific research offers particularly elegant parallels to the Monty Hall problem. A researcher develops several hypotheses to explain a phenomenon and initially favors one based on theoretical considerations or preliminary evidence. Subsequent experiments rule out some hypotheses while leaving others viable. Should the researcher continue investigating her original favorite hypothesis, or should she shift attention to alternatives that haven't been falsified? The philosophy of science suggests that unfalsified hypotheses become more credible as alternatives are eliminated, much like the remaining door in the Monty Hall problem gains credibility when the host eliminates one of the alternatives. Even in everyday decision-making, Monty Hall principles frequently apply. When choosing between restaurants, job offers, or potential romantic partners, people often make initial preferences based on limited information. As more information becomes available, perhaps negative reviews about some restaurants, or some job offers being withdrawn, the question arises whether to stick with original preferences or switch to alternatives that remain viable. Understanding the logic of conditional probability can improve these everyday decisions by helping people recognize when new information should lead to preference reversals and when it shouldn't. The Monty Hall problem opens a window into the broader mathematical theory of uncertainty, a field that encompasses far more than simple probability calculations. Modern mathematics has developed sophisticated tools for reasoning about different types of uncertainty, from the randomness of quantum mechanics to the ambiguity of natural language to the incompleteness of information in complex systems. The insights we gain from carefully analyzing the Monty Hall problem provide foundation for understanding these more advanced topics, revealing how mathematical precision can illuminate even the most uncertain aspects of our experience. Classical probability theory, as illustrated by the Monty Hall problem, deals with situations where we know the possible outcomes and their associated probabilities. This framework works well for games of chance, controlled experiments, and other scenarios where the structure of uncertainty is well defined, but many real-world situations involve deeper layers of uncertainty. We might not know what the possible outcomes are, or we might be uncertain about the probabilities themselves, or we might face genuine ambiguity about how to model the situation mathematically. These more complex forms of uncertainty require mathematical tools that go beyond classical probability theory. One important extension is the theory of imprecise probabilities, which deals with situations where we cannot assign exact numerical probabilities to events. Instead of saying that an event has probability 0, 6, we might only be able to say that its probability lies somewhere between 0, 4 and 0, 8. This imprecision might reflect genuine limitations in our knowledge, disagreement among experts, or fundamental ambiguity in the situation itself. The mathematics of imprecise probabilities provides tools for making rational decisions, even when our uncertainty cannot be captured by precise numerical probabilities. Another important extension is the theory of fuzzy sets and fuzzy logic, which deals with situations where the boundaries between categories are unclear or gradual rather than sharp. Classical logic deals with statements that are either true or false, and classical probability assigns numerical degrees of belief to such statements. But many real-world concepts like tall person or good investment or effective treatment have fuzzy boundaries that resist crisp classification. Fuzzy mathematics provides tools for reasoning about these imprecise concepts while maintaining mathematical rigor and precision. Information theory, which we discussed earlier in the context of the Monty Hall problem, extends into even more abstract territories when dealing with complex systems and communications. The concept of entropy, originally developed to quantify uncertainty in probability distributions, has found applications in physics where it measures thermodynamic disorder, computer science where it measures information content, and even biology where it helps analyze the complexity of genetic codes. These applications show how mathematical concepts developed for simple probability problems can illuminate fundamental aspects of the physical and biological world. The Monty Hall problem, despite its simple appearance, connects to deep questions in computer science about computational complexity and algorithmic efficiency. While the problem itself can be solved with elementary probability theory, variations and extensions of the problem lead to computational challenges that illuminate fundamental principles of algorithm design and analysis. Understanding these connections helps bridge the gap between mathematical reasoning and computational thinking, showing how problems that seem purely theoretical can have important implications for practical computing and artificial intelligence. Consider a generalized version of the Monty Hall problem where there are n doors instead of 3, and the host opens k doors before offering the switch. How should we compute the optimal strategy as n and k grow large? The naive approach of enumerating all possible scenarios becomes computationally infeasible as the numbers grow, since the number of scenarios grows exponentially with n. This forces us to develop more efficient algorithms that exploit the mathematical structure of the problem rather than relying on brute force enumeration. The efficient solution involves recognizing that the problem has a recursive structure. The optimal strategy for n doors can be computed from the optimal strategy for smaller numbers of doors. This insight leads to dynamic programming algorithms that solve the problem in polynomial time rather than exponential time. The same algorithmic techniques that make the generalized Monty Hall problem computationally tractable also apply to many other optimization problems in computer science. From finding shortest paths in networks to scheduling tasks on computers to optimizing investment portfolios, machine learning provides another computational perspective on the Monty Hall problem. Instead of deriving the optimal strategy through mathematical analysis, we might try to learn it from experience. A reinforcement learning algorithm could play millions of simulated games, gradually discovering through trial and error that switching doors leads to better outcomes than staying. This approach raises interesting questions about the relationship between mathematical proof and empirical learning. Can computational agents discover mathematical truths through experience, even without understanding the underlying theoretical principles? The computational perspective also illuminates the robustness of the Monty Hall strategy to various forms of uncertainty and noise. In real-world implementations, the host might not always follow the prescribed protocol exactly, the door mechanisms might malfunction occasionally, or the contestant might misunderstand the rules. How sensitive is the switching advantage to these kinds of implementation errors? Computer simulations can explore these questions systematically, revealing which aspects of the problem are crucial for maintaining the optimal strategy and which are merely incidental details. An intriguing extension of the Monty Hall problem emerges when we consider it in social contexts where multiple players interact and influence each other's decisions. What happens when contestants can observe previous players' choices and outcomes? How do social learning and conformity pressures affect the discovery and adoption of optimal strategies? These questions transform the individual decision problem into a study of collective intelligence and social dynamics, revealing how mathematical truths spread through communities and how social factors can either accelerate or impede the adoption of optimal strategies. Imagine a scenario where contestants on a game show can observe the choices and outcomes of previous contestants before making their own decisions. Early contestants, lacking historical data, might rely on intuition and choose suboptimally, but as data accumulates, later contestants have the opportunity to learn from previous experiences and discover the switching advantage through observation rather than mathematical analysis. Computer simulations of this social learning process reveal interesting dynamics. The community gradually converges toward optimal play, but the speed of convergence depends on various factors, including how much weight contestants place on recent versus distant historical evidence. Social influence complicates this learning process in realistic ways. Contestants might be influenced not just by the objective outcomes they observe, but also by the apparent confidence and expertise of previous players. If early contestants who stay with their original doors happen to win through luck, this might create misleading social proof that staying is the better strategy. Conversely, if respected authority figures publicly endorse the switching strategy, this might accelerate its adoption even among people who don't fully understand the underlying mathematics. These social dynamics show how the spread of mathematical knowledge through communities depends on more than just the logical force of mathematical arguments. The network structure of social influence also matters. In some communities, people primarily learn from immediate friends and family members, creating local clusters of belief that might persist even when they're suboptimal. In other communities, people learn from diverse sources including experts and strangers, creating more efficient information aggregation. Social media and online forums represent new types of learning networks where information can spread rapidly across traditional social boundaries, but where it might also become distorted or polarized in unexpected ways. These social dynamics have implications far beyond game shows. The same mechanisms that affect how optimal strategies spread in artificial game environments also influence how scientific knowledge, medical practices, financial strategies, and technological innovations diffuse through real communities. Understanding these processes can help design better institutions for promoting the adoption of beneficial practices while preventing the spread of harmful misinformation. The Monty Hall problem, seemingly a simple puzzle about doors and goats, opens up profound philosophical questions about the nature of knowledge, rationality, and truth. When we say that switching doors is the correct strategy, what exactly do we mean by correctness? Are we making a claim about objective mathematical reality, or are we describing the best choice for a particular type of rational agent with specific goals and beliefs? These questions connect the practical puzzle to deep philosophical issues that have occupied thinkers for centuries, revealing how even elementary mathematical problems can illuminate fundamental questions about reasoning, reality, and human knowledge. The problem raises important questions about the relationship between mathematical truth and practical wisdom. The mathematical analysis clearly shows that switching maximizes the probability of winning the car. But what if the contestant doesn't particularly want the car? What if they would prefer the goat, either for personal reasons or because they object to the materialistic values implied by preferring an expensive car over a living animal? The mathematical correctness of switching depends on assuming that winning the car is the contestant's goal, but this assumption might be questioned on practical or ethical grounds. Even more fundamentally, the problem illuminates questions about the nature of rationality itself. What does it mean to be rational in situations involving uncertainty? The standard economic model assumes that rational agents maximize expected utility based on their beliefs and preferences. Under this definition, switching doors is rational because it maximizes the expected probability of achieving the assumed goal, but alternative conceptions of rationality might emphasize different criteria. Perhaps rationality requires consistency with one's past choices, or conformity with social norms, or adherence to principles that can be universally applied. The Monty Hall problem also raises epistemological questions about how we can know what we know. The mathematical proof that switching is optimal relies on various assumptions: that the game follows the stated rules, that the host has perfect knowledge, that probabilities represent objective features of the world rather than subjective degrees of belief. Each of these assumptions might be questioned, leading to different conclusions about optimal strategy. This highlights a general feature of mathematical reasoning. Its conclusions are only as reliable as the assumptions on which it's based. Perhaps most intriguingly, the problem connects to questions about the relationship between individual and collective reasoning. While mathematical analysis reveals the optimal individual strategy, what happens when everyone knows this analysis? If all contestants switch doors, does this change the nature of the game or the optimal strategy? These questions about common knowledge and strategic sophistication connect the elementary probability problem to advanced topics in game theory and social epistemology. The Monty Hall problem didn't emerge in a cultural vacuum. Its formulation, popularization, and interpretation reflect broader cultural attitudes toward probability, mathematics, and rational decision-making. Understanding the cultural context of the problem helps explain why it became such a phenomenon in late 20th century America and why it continues to fascinate people across different societies. The problem's cultural resonance reveals something important about how mathematical ideas interact with broader social values and assumptions about knowledge, expertise, and authority. The problem emerged during a period when television game shows were a dominant form of popular entertainment in America. Shows like Let's Make a Deal represented a particular cultural moment when the possibility of sudden wealth through luck and clever decision-making captured the public imagination. The Monty Hall problem crystallizes this cultural fascination with chance and choice, transforming the entertainment spectacle into a precise mathematical question. In a sense, the problem represents the mathematization of American dreams about luck, opportunity, and the possibility of beating the system through superior reasoning. The controversy surrounding Marilyn Vosavant's correct solution also reflects broader cultural tensions about intellectual authority and expertise. The fact that so many highly educated people initially rejected her answer reveals anxieties about who gets to be considered a mathematical authority, particularly when that authority challenges conventional wisdom. The gendered dimension of the controversy, with several critics suggesting that women might think about mathematics differently than men, reflects broader cultural stereotypes about mathematical ability and reasoning styles. Different cultures might approach the Monty Hall problem with different intuitions and assumptions. Cultures that emphasize collective decision-making over individual choice might find the problem's focus on solitary optimization less compelling. Societies with different attitudes toward gambling, risk-taking, or material acquisition might question the problem's implicit assumptions about what constitutes a desirable outcome. These cultural variations suggest that mathematical problems, even seemingly objective ones, are interpreted through cultural lenses that affect their meaning and significance. The problem's continued popularity in the internet age reflects new cultural dynamics around viral intellectual content and the democratization of mathematical knowledge. Online forums, videos, and interactive simulations have made sophisticated mathematical concepts accessible to much broader audiences than traditional academic channels could reach. The Monty Hall problem benefits from this new media ecosystem because it combines mathematical sophistication with intuitive accessibility, making it ideal for the kind of intellectual entertainment that thrives in digital environments. The Monty Hall problem also raises epistemological questions about how we can know what we know. The mathematical proof that switching is optimal relies on various assumptions: that the game follows the stated rules, that the host has perfect knowledge, that probabilities represent objective features of the world rather than subjective degrees of belief. Each of these assumptions might be questioned, leading to different conclusions about optimal strategy. This highlights a general feature of mathematical reasoning. Its conclusions are only as reliable as the assumptions on which it's based. Perhaps most intriguingly, the problem connects to questions about the relationship between individual and collective reasoning. While mathematical analysis reveals the optimal individual strategy, what happens when everyone knows this analysis? If all contestants switch doors, does this change the nature of the game or the optimal strategy? These questions about common knowledge and strategic sophistication connect the elementary probability problem to advanced topics in game theory and social epistemology. The Monty Hall problem didn't emerge in a cultural vacuum. Its formulation, popularization, and interpretation reflect broader cultural attitudes toward probability, mathematics, and rational decision-making. Understanding the cultural context of the problem helps explain why it became such a phenomenon in late 20th century America and why it continues to fascinate people across different societies. The problem's cultural resonance reveals something important about how mathematical ideas interact with broader social values and assumptions about knowledge, expertise, and authority. The problem emerged during a period when television game shows were a dominant form of popular entertainment in America. Shows like Let's Make a Deal represented a particular cultural moment when the possibility of sudden wealth through luck and clever decision-making captured the public imagination. The Monty Hall problem crystallizes this cultural fascination with chance and choice, transforming the entertainment spectacle into a precise mathematical question. In a sense, the problem represents the mathematization of American dreams about luck, opportunity, and the possibility of beating the system through superior reasoning. The controversy surrounding Marilyn Vosavant's correct solution also reflects broader cultural tensions about intellectual authority and expertise. The fact that so many highly educated people initially rejected her answer reveals anxieties about who gets to be considered a mathematical authority, particularly when that authority challenges conventional wisdom. The gendered dimension of the controversy, with several critics suggesting that women might think about mathematics differently than men, reflects broader cultural stereotypes about mathematical ability and reasoning styles. Different cultures might approach the Monty Hall problem with different intuitions and assumptions. Cultures that emphasize collective decision-making over individual choice might find the problem's focus on solitary optimization less compelling. Societies with different attitudes toward gambling, risk-taking, or material acquisition might question the problem's implicit assumptions about what constitutes a desirable outcome. These cultural variations suggest that mathematical problems, even seemingly objective ones, are interpreted through cultural lenses that affect their meaning and significance. The problem's continued popularity in the internet age reflects new cultural dynamics around viral intellectual content and the democratization of mathematical knowledge. Online forums, videos, and interactive simulations have made sophisticated mathematical concepts accessible to much broader audiences than traditional academic channels could reach. The Monty Hall problem benefits from this new media ecosystem because it combines mathematical sophistication with intuitive accessibility, making it ideal for the kind of intellectual entertainment that thrives in digital environments. While the basic Monty Hall problem has been thoroughly analyzed and understood, it continues to inspire new research directions and open questions that push the boundaries of probability theory, decision science, and cognitive psychology. These future directions show how a simple puzzle can serve as a launching point for sophisticated research programs that advance our understanding of uncertainty, reasoning, and choice. The problem's enduring research value lies not in its original formulation but in its capacity to generate new questions and insights as our mathematical and scientific tools become more sophisticated. One active area of research involved extending the Monty Hall framework to more complex scenarios with multiple players, evolving rules, or incomplete information. What happens when multiple contestants must coordinate their choices? How does the optimal strategy change when the rules of the game evolve based on previous outcomes? These questions connect to broader research programs in mechanism design and dynamic games, where mathematicians and economists study how to design systems that promote desirable outcomes through appropriate incentive structures. Another promising direction involves investigating the neural and cognitive mechanisms underlying human performance on Monty Hall-style problems. Modern neuroscience techniques like fMRI and EEG allow researchers to observe brain activity while people solve probability problems, potentially revealing why these problems are so difficult for human intuition. Understanding the neural basis of probabilistic reasoning could inform both theoretical questions about human rationality and practical questions about how to design better educational interventions. Artificial intelligence research provides yet another lens for studying the Monty Hall problem and its extensions. As AI systems become more sophisticated, researchers are interested in whether they develop human-like biases when reasoning about probability, or whether they discover novel solution strategies that humans haven't considered. Machine learning systems trained on large datasets of human choices might reveal subtle patterns in how people actually make decisions in uncertain situations, going beyond what laboratory experiments can uncover. The problem also connects to frontier questions in quantum mechanics and quantum information theory. Quantum versions of the Monty Hall problem have been proposed where the doors exist in superposition states until observed, leading to new types of optimal strategies that exploit quantum mechanical effects. These quantum extensions might seem purely theoretical, but they could have practical implications for quantum computing and quantum cryptography as these technologies mature. And so we reach the end of our gentle wandering through the mathematical landscape of the Monty Hall problem and its many fascinating extensions. We've explored how a simple game show puzzle opens up entire worlds of mathematical beauty, from the elegant simplicities of conditional probability to the complex dynamics of social learning and cultural interpretation. Along the way, we've discovered that mathematics isn't just about numbers and formulas. It's about ways of thinking that can illuminate the deepest questions about knowledge, choice, and uncertainty that we face as human beings navigating an uncertain world. The Monty Hall problem teaches us that mathematical truth can hide behind the most innocent-seeming situations, waiting to surprise us with insights that contradict our deepest intuitions. It reminds us that rational thinking often requires the humility to question our first instincts, and the patience to work through complex reasoning even when simpler answers seem obviously correct. Perhaps most importantly, it shows us that mathematics at its best isn't cold or mechanical, but rather a warm and human endeavor that helps us make better sense of the beautiful complexity of existence. As you settle into sleep tonight, perhaps you'll carry with you some of the gentle wonder we've explored together. Maybe you'll dream of doors opening to reveal not goats or cars, but new possibilities for understanding the intricate dance between certainty and uncertainty that shapes every moment of our lives. The mathematics we've shared tonight isn't just about solving puzzles. It's about developing the mental tools and perspectives that can make us more thoughtful, more humble, and more wise as we face the countless choices that lie ahead of us. Sweet dreams, fellow travelers in the realm of mathematical curiosity. May your rest be peaceful, and may tomorrow bring new opportunities to discover the hidden mathematical wonders that surround us always, waiting patiently for minds curious enough to notice them and hearts gentle enough to appreciate their quiet beauty.